Good afternoon, and welcome to our webinar on indoor air quality in commercial spaces, sponsored by AHRI and BOMA. Obviously, this is an extremely timely topic, and we're very pleased to have with us a distinguished lineup of speakers today. America's HVACR and water heating industry, from the equipment manufacturers to the distributors to the installers and maintainers, and America's building owners and managers, are committed to providing and implementing the technologies that can make commercial buildings as safe and health affirming as they can be. I'm Francis Dietz, Vice President of Public Affairs at AHRI, and with me is my counterpart at BOMA, Don Davis, who is Vice President of Advocacy and Codes. We have a distinguished lineup of speakers today. I will introduce Ron Cosby from AHRI member company Trane Technologies, and then I will turn it over to Don Davis to introduce our other two panelists. Before we get into the program, I would like to let you know that if you have questions, you can submit them through the Q&A feature at the bottom of your screen, and we will get to as many as we can at the end. As technology and thermal systems leader at Trane Technologies, Ron Cosby is responsible for overseeing his company's technological development of the Americas commercial HVAC products and services. During his 20+ years at Trane Technologies, he has managed the design and quality of heating and cooling systems, has reviewed and directed internal technology development, and leveraged and assessed external technologies to bring clean, reliable, conditioned air and water solutions to customers. In his current position, he helps to apply his expertise in indoor air quality to assess commercial air systems components and offerings to ensure proper humidity levels, enhanced ventilation, and air cleaning for customers. Prior to joining Trane Technologies, Ron worked as a combustion engineer for Roper GE Appliances. Ron holds a bachelor's degree in aeronautical and astronautical engineering and a master's degree in mechanical engineering, both from Purdue University. I will now turn it over to Don Davis to introduce our other two panelists.
Oh, thank you, Francis. On behalf of BOMA International and AHRI, I want to thank you for taking the time to join us today for this important discussion on indoor air quality. With the reopening of offices and the need to ensure comfort, safety, and what I think is most important, the confidence in the health of the indoor environment, we believe that the information provided by all the speakers today will be of great importance to BOMA members and AHRI members alike. Today I have the opportunity to introduce Guy Tomberlin from International Code Council and Ernest Conrad of Conrad Consulting. And both are thought leaders in the area of indoor air quality and indoor environmental quality. Guy Tomberlin is the Vice President of Plumbing, Mechanical, and Gas Programs, including swimming pools, with the International Code Council. Prior to 2020, Guy worked with the building department within Fairfax County, Virginia for 34 years. During that time, he served as the plumbing inspector, combination inspector, supervisor of mechanical inspections, chief of permitting branch, chief plumbing inspector, and retired as the chief of commercial and residential building inspections. He has more than 30 years of experience working in codes and standard development on a national, state, and local level. For most of his career, Guy has served as a code inspector on PMG courses across the country and beyond. He is a Virginia State Master Plumber, HVAC, gas fitter, and black flow protection device worker. He also maintains several ICC certifications in inspection and plane review, along with being certified building CPO, plumbing, mechanical, and property maintenance official. Our final speaker will be Ernest Conrad. Mr. Conrad is the principal in charge of Ernest Conrad Consulting. It's a professional engineering consulting firm which focuses its services on building, mechanical, electrical, plumbing, and fire protection systems and operations. He has over 30 years of experience in engineering expertise in environmental systems, problem solving focused on achieving a balance of occupant comfort and building content protection while achieving efficient operating levels. Mr. Conrad specializes in conducting building inspections to assess environmental improvements and identification of thermal or moisture deficiency in the building envelope. As a CEM, Mr. Conrad is qualified to perform formal ASHRAE energy audits and design and implement MEP improvements in all buildings, including commercial, residential, religious, and historically significant structures. With that, I'd like to turn it over to Ron Crosby to begin the session. So Ron.
I apologize. It's actually not Ron. It's Ernie. Sorry. Go ahead, Ernie.
Thank you very much, Francis. My name is Ernest Conrad, and today I'm going to address indoor air quality from a scientific viewpoint. And what I will do is I get these slides to move along. First, here we go. Okay, first, as an agenda, I will touch on applicable codes and standards. Then we'll discuss physical characteristics of various organisms, followed by particulate filtration mechanisms. And then we'll talk about various approaches to devices for particle control. So with that, codes and standards. There are two primary standards that are intended to promote good indoor air quality. The first is Ashtray Standard 62.1, and it intends to improve indoor air quality by mandating a minimum amount of outdoor air into a building. And that minimum is either 5 CFM per person, that's cubic feet per minute, minimum, or it has another method which is called the ventilation rate procedure, which is a calculation based on dilution ventilation and treatment of other indoor pollutants. Okay. The second is Ashtray Standard 55. And Ashtray Standard 55 is a theoretical human comfort chart. And as you can see on the chart, if you're a person who is in the environment, which is between maybe 70 and 80 degrees Fahrenheit and 30 to 50% relative humidity, you are by definition a comfortable person. And a big part of indoor air quality is in fact to have human comfort. It's a very important piece of the equation. Next. Okay, this is a physical characteristics of organisms chart. These are properties of various different aerosols. And as you can see, it ranges from the small particles as molecular sizes, all the way up to beach-sized particles. And I know this is kind of hard to look at, so what I'm going to do is to make it a little bit easier. But this is based on a unit of measure called a micron. And 1 micron is equal to about 1 millimeter. So it's 1 millimeter is about 1,000 microns. And if we look at some of the typical particle sizes, the human hair is about 100 microns. If we can see, I'm not sure. But anyway, I'll explain it to you. The human hair is about 100 microns in diameter. And tobacco smoke is ranges between 0.01 to about 10 microns in size. And if you look at the virus, the particle size of a virus ranges between 0.003 to about 0.03 microns. And if you think about that, the virus particle is so small, this is 30,000 times smaller than a particle size of tobacco smoke. If you think of tobacco smoke as a tiny, tiny particle, it lays in the air, it doesn't settle to the ground, and a virus is 30,000 times smaller than that. And this is why it's so difficult to deal with viruses, because the size of the particle so incredibly small. And you think about plant spores or mold spores, they're usually between 10 and 30 microns. So they will basically settle out to the floor. Bacteria then is about, it ranges between 0.3 to about 30 microns in size. And these particles are larger than tobacco smoke, but at the same time, they need to have a surface to attach to. So you'll find them attached to water droplets, other types of organic materials. So you'll find bacteria in the form of being attached to other things. And the last but not least is the Hepa filter. The Hepa filter is high efficiency particulate air. And I'll give you just some examples of, if the next slide, please. This is a filtration effectiveness chart. And the way it works is, some years ago, we used to have particle efficiencies on air filters, and we used what's called the dust spot method. We don't use that method anymore, but what it did was it said a typical 1-inch throwaway filter for an HVAC system is about 30% efficient. And today that is equivalent to what we call a MERV 8. And MERV is mean efficiency rating value. That's what the MERV stands for, okay? And typically, if we have a modern Class A office building, we'll find efficiencies of between 60 and 80% using the dust spot method. When that range is 60% is about a MERV of 11. And interesting, you might notice that in New York City, where I'm a regular, the city council has created a law a couple of years ago. This is the minimum amount of filtration of all air coming into a building from minimum outside air requirements has to be MERV 11. So all of our office buildings now in New York City have a minimum air filtration rate of MERV 11, which is about 60 to 65% efficient by dust spot method. And the other is in our more modern office buildings, we use efficiencies up around 80, 85%, and that's equivalent to a MERV 13. And as you probably all well know, that CDC now says the MERV 13 filter is the standard for virus control. And now they're mandating this throughout the country in all buildings. So all of us now are targeting a MERV 13 rating, which gives you a filtration rating. You can't quite see it here, but it's about 90% of particle sizes smaller than about 1 micron. And that's the MERV 13. And the other larger one is if you get into high efficiency, we start talking about MERV 17 or the HEPA, high efficiency particulate air. These are the filters that will take out 99.97% of particles smaller than 0.1 microns in size. Okay, next slide, please. And some simple things we can do for control of particulates in our buildings. Walk-off mats. This is a great way to keep particulate out of the building and minimize its introduction into the breathing zone within our office buildings. So this is a great simple thing people can do. There's lots of other simple things as well as that. Next slide. And there's things a little bit more complicated, but it's very popular now in Class A office buildings. We have systems called DOAS, Dedicated Outdoor Air Systems. And what this equipment does, it sits on the top of a building and it takes the code required minimum outside air and it will precondition that air. It'll heat it, it'll cool it, it'll humidify it, it'll filter it to great high efficiency levels, and then introduce it into the air as a means of maintaining good indoor air quality. And the next slide. Just examples of other types of filtration devices we can use. These are MERV 11, MERV 13, but this is activated carbon. Activated carbon is a great mechanism for removing volatile organic compounds. It can remove vehicle exhaust. If you're in an urban environment area, you'll find a lot of unburned hydrocarbons and vehicle exhaust, which gets into the building, and this carbon will react with it and filter it out of the airstream. The next slide, please. And the other one is popular, as you'll find, this is smaller cartridge type filter, but they has carbon impregnated filter for your HVAC systems. These are usually about a 2 or 3 inch thick, medium efficiency, 80–85% efficient, and it removes the carbon, and it does a very good job in taking out things from the environment outside of your building. And next slide. And the other thing we have now is we have devices called electrostatic ionizers. These are popular to put in a room. It's a self-contained device, and what they do is they will put an electrostatic charge on the airstream within the environment, and that will attach onto other particles in the airstream and agglomerate with them, get heavier, and fall to the floor. And the idea is that it removes particles from your breathing zone before they get to your breathing zone. We also have to be careful. These things also generate ozone. Ozone is an O3 radical. It's not regulated in the United States, but it's regulated in all the other countries. So we need to be careful that if we do use these devices, to be very sure we have equipment we buy that's regulated by the industry to try and prevent having ozone generation as a byproduct of these electrostatic ionizers. And with that, I will pass it on to Guy.
Good afternoon, and thank you all very much for allowing me to come be with you today and talk a little bit about the International Code Council and the mechanical codes associated with indoor air quality. Next slide. Today we're going to, there you go. Today we're going to talk about what we're talking about is the new normal. So I mentioned it several times, and as you see through the presentation, that's more a tongue-in-cheek term. At the end of this, you'll see how these 3 presentations tie together and how the building code impacts or may not impact the application that you're dealing with. So we're talking about what is the new normal. We're going to describe it. We're going to evaluate it. And we're going to try and more clearly understand how these systems are operating and what can improve the indoor air quality, and what happens when you determine that you are going to change the indoor air quality of a system, and how you're going to incorporate it into the existing system you're working with. So what's the definition of new normal for air quality? You know, the reality is there's really not one size that's going to fit all, and there's no silver bullet. Indoor air quality is going to be based on several different things that you're familiar with in your particular application. And these are things like, what's the type of the structure? What's the occupancy that's being, the structure's being used for? What's the existing equipment look like? And how does it operate? And what does it do? The needs of the occupants and the ability to alter the equipment and the practices that are being used at the time. So I put these 3 kind of, character animated type of buildings on the right-hand side, just to try and get creative thoughts and processes moving early on in the presentation. You take a drive-through cafe, for example. You got a window that's constantly opening and closing while you have people sitting in a dining area that's trying to maintain their air quality the same as the person that works at the window. And you might even have another part of the operation that's maybe a store in there that has an entirely different application for indoor air quality. Firehouses, I always feel is a great example for how diversified indoor air quality is going to be. If you think about it for 1 minute, the bays where the vehicles are parked, they generally operate off diesel fuel vehicles, the majority of them. And so you've got that area that has to be maintained. Then you have the ambulances that typically have medicines that might need to be tempered. The temperature might have to change a little bit for things that might be stored in those vehicles. Then you move over into the sleeping quarters for the employees. Then you have office space for the employees, administrative space. And so you have all these different types of facilities, and then you probably have a weight room that might be in there as well, an activity area. So you can only imagine things change, and how you have to deal with each one of these areas is going to be quite different. This example is on the far right, right above BOMA, and that's the multi-purpose facility. And I don't know what this is. This is just a building that looks like it could have a lot of different activities going on. You might be familiar with, like in the back left corner, that could easily be a medical facility. And moving over, towards the right, from left to right, you could have an activity part that might be a swimming pool. You could move over further, and the next area might be an activity weightlifting center or something like that. Then on the far right could easily be a community center. Up in the top left could easily be like office spaces. So assessing these types of equipment that are going to be serving each one of these spaces, do you have one piece of equipment that serves multiple spaces, or do you have multiple pieces of equipment that serve each one of the spaces? And then, if it's a medical facility, you see one of the bullets talks about the needs of the occupants. You may have the need for a little bit elevated air quality in some of those particular applications. So I hope that kind of illustrates a little bit where we're going with some of these examples we talk about today. Next slide, please. So the new normal is going to be different for everybody. I guess that's what I'm trying to say. So quite frankly, there really is not a new normal. It's really what's going to be your new normal for operation for your particular application. Some folks might want to be able to replace their equipment or upgrade it or retrofit existing systems. Some of you might already have state-of-the-art equipment, and in that case, your focus is going to be on maintenance and operation to ensure that you maintain that state-of-the-art equipment. And then others of you might learn that changing some of these systems is a little more challenging than you originally expected. And I use the illustrations across the bottom again. Bottom left could easily be a high school front or something like that, or it could be an office space. Any one of the two. The moving over left to right, the next building on the top, it has the brick front on it, partial brick front. That's what's become very popular in marketplace type construction today, where you can have drugstores and big box stores and living spaces and business occupancies, office spaces, all in the same building under the same roof. And then on the left could easily be a parking garage as well. So you've got these systems that you have to figure out how are they all going to integrate together and how are they going to operate best. But the one, if you move over two to the right, that building that the arrow is on now, the dark brown building looks like it could easily be an older building. And in that case, the two on the right-hand side are buildings that may have been built in the early 1900s, mid 1900s, and they might have been retrofitted 2 or 3 times, 4 times by now. And now you have to deal with an older structure that's got newer systems in them and trying to figure out how to make all that stuff work together. So the point I'm making here, and Ron will talk a little bit more about in his piece, is making sure that you look at these systems holistically, that they're all one big system. Next slide, please. What do the codes have to do with it anyway? I'm going to talk about the 3 basic mechanical codes that are out that the International Code Council publishes. It's the mechanical code, the IMC we'll call it, the existing building code, and the International Property Maintenance Code. So these are the 3 we'll highlight quickly. I'll run through them briefly. Next slide, please. The first one's a mechanical code, and Ernie talked a little bit about ASHRAE 62. The mechanical code is for new construction, design, engineering, and installation for HVAC mechanical systems. The reason ASHRAE 62 is important is the outdoor air requirements are clearly outlined in the IMC, and for all the different types of occupancies and the square footage and the efficiency of the system. That's how all these outdoor air calculations are performed. So all this has to be taken into consideration to determine what the best and most efficient air quality is for the particular space. And it's an air balance is required at the end. And I put that in this particular segment here because I want to touch back on it again in a minute, and you'll understand a little more why that's so important. The original permitting information, if you have an area that adopts, the international codes, you would want to go back and find out what edition the IMC, was used when the building was built. And that's extremely important. So when you find out what that is, that's where you can begin your evaluation, because you don't know if you have, an older type system that's designed to do one thing or a newer type system that's designed to do another. So that it is critically important if you're thinking of undertaking a big rehabilitation project. Next slide, please. So again, I'm going to elaborate a little more why that original design is so important. Some people think, hey, we've got a 5-year-old building. It meets current code requirements. Everything's fine. We've got the best and latest, greatest, equipment out there. Nothing, we don't need to make any adjustments. That's not 100% accurate. If you got a building that's five or 6 years old, it could easily be 2 or 3 code editions previous. So right now we've got published the 2021 codes, and they're published every 3 years. So you could see some changes from your building design for as recently as 3 years ago. And more importantly, you'll notice I have a smoking symbol in the bottom there with a line through it. If you go back, some of these buildings are decades old, the designs. If you have a building that was built perhaps in the early 90s, you could easily have outdoor air ventilation systems that incorporated smoking activities, which changed things as well. And all those designs came from Ashtray 62, and that has changed tremendously over the past 30 years from those later 80 additions to currently now where smoking is just a single type occupancy, not a general concept in a building. So the last thing in looking at the original design is, you might have the same tenants in the building, but they might have moved around. And things like conference rooms, for example, require more airflow and require more outside air. So if a tenant took out 2 office spaces and created a nice conference room, it might have had a lot less airflow coming through those spaces when they were offices, and they might not have updated the requirements for what the new use would be. So it's important to know what's there. So they might not just be moving out of the building, and getting a new tenant in there. This could be, the tenants that you already have in there kind of doing their own thing and moving things around. So it's important to understand how that works together with what I'm going to talk about for the rest of the presentation. Next slide. The next code is, so hey, you've got an existing building, you've determined you want to make some upgrades. You go to the International Existing Building Code. That identifies 3 different levels of construction. One's pretty basic maintenance, replacement type of operations. One up to level 3, which is going to be your fully renovated type of operation, and that will probably throw you back into the requirements of the new current IMC. So it's very, very closely mirrors that for the higher grade construction level. But in any case, no matter what you're doing, you want to make sure you're checking for permits and determining if those are going to be necessary. Next slide. So property maintenance is pretty basic, and it just says, hey, you got to have a system that's operating safely and it can perform its intended function. Duct systems are basically the same. You just can't have any obstructions in them, and they have to be capable of operating to the intended function. So to make sure that you have the clear basic system that you started with, these are a couple of the things that you have to keep in mind. And what I want to point out here is building codes are written on minimums, not maximums. So now you've established and you've gone back and you found original blueprints and drawings, and you might find out that, hey, this is a great system, works perfectly well, meets all of the current code requirements, health, safety, and welfare of the occupants and the people that are visiting. But it could be improved. So now you're talking about how you might want to do different types of enhancements to the existing systems. So that's what I'll get into for the last part of my presentation. Next slide, please. When are permits required? If you're doing alterations to the required HVAC equipment, the equipment that has to be there, that's serving the function to bring outside air in. Ernie showed a great illustration of an outside air unit that certainly a unit like that one on that roof would, if you were installing something like that, you'd probably have a crane out there. It's got structural components, it's got electrical components, and it's got HVAC components. So you're probably going to need permits for that. If you're putting additional equipment in, he showed some different types of filtration methods. Those types of things, I've got a little small electrical outlet up on the right-hand side of this slide, just to let you know that it's not always HVAC that triggers the permit requirement. You might be altering the electric circuitry in the building, and you might need to get a permit for that as well. Just adding some exhaust, maybe you're getting more makeup in a room, maybe you're trying to create more airflow and circulation in a room. If they're permanently installed, those types of things are probably going to need permitting. Electronic filtration, again, if you're altering the electronic system, or you're replacing the existing filtration system, that might need a second set of eyes. I wrote across the bottom, just make sure you contact whoever's in charge of the permitting and the inspection department and ask them, let them know what you're doing and find out if that's the way you need to go or not. Humidifiers may have plumbing connections as well, and so you have to you might need to get a plumbing permit for that, as well as an electrical. And at the bottom one I put, if you're putting new equipment in altogether, new appliances and equipment, not only will you probably need a permit, you might need a set of plans as well, and you might have to go back and try and do some of those calculations on those outside air requirements. So it's extremely important to understand when permits are required. Next slide. So when a permit's not required, when you're using some of these cord and plug units that are removable, air purifiers, room humidifiers, and just room fans and things like that. I did put a note down there at the bottom. Hey, keep in mind that some of these systems do impact your performance of your existing systems. And I think Ron's going to share with you in a moment about how humidity does impact your airflow system and the importance of it. So just keep that in mind. You know, sizing for HVAC equipment sometimes is contingent on the amount of humidity and outside air that gets introduced into the system. So again, contact the local jurisdiction, find out what you need on permitting and plan review, and they'll set, help you the right direction on that. Next slide. In summary, I'm doing perfect on time. So Ron's got a great elaborate, detailed presentation. I was kind of trying to stay at the high level of keeping track of where you might need a permit, where you might need a second set of eyes in there when you do these evaluations. Keep in mind to look at these systems holistically, determine what you plan to do with it. Are you going to leave it the same, or are you going to try and do some type of retrofitting or alterations to it? And then you're going to determine which codes and standards are applicable. Ernie talked about a couple standards earlier. You might want to look at those for more detailed installations, for more specific applications. And then again, check with the local jurisdiction to figure out if permitting and plan submissions are needed. And lastly, I didn't talk too much about this other than the air balance. Commissioning is extremely important if you're going to upgrade the entire system to make sure it's working as intended, and at least know that we're going to start off with the new system as working correctly and getting the desired level of air quality into each one of the spaces that you're taking care of. So thanks for having me today, and look forward to the question and answers in the end. And I'm going to turn this over to Ron Cosby right now.
All right, good afternoon. So thank you for allowing me to talk hopefully about some insight that we see for the future of building IAQ. I want to build upon what Ernie and Guy have talked about here, just to show you what you can do as a building owner or manager. So let's go back. Guy talked about every space is unique. What you need to do is you need to ensure that the systems in your buildings are working together just to make sure you get that desired outcome for risk reduction from an IAQ perspective. You really shouldn't look at this as a single instance in time, though. You want this to be an ongoing process that can lead to just an overall high quality environment for your building. We've been doing that with really looking at 3 tenets of IAQ, and that's assess, mitigate, and then manage. So I'll talk about each one of those here on the subsequent slides. So Francis, if you can move forward. So let's talk about assessment first. So why should you assess your building? Well, the first thing you need to do is really figure out where your building is today. If you don't know where your building is today, you can't really strategize on where you want it to go. So that assessment is there to help you baseline what you really need and develop a plan to mitigate any type of indoor air quality issues. So that assessment's really a key planning step to get you to where you want to be and your potential occupants so that they have the confidence that they can come back into the building. So when we've been talking to customers around that IAQ assessment, we've been using it with 4 pillars of mitigation, and those are dilute, exhaust, contain, and clean. And if we go to the next slide, we'll talk about those pillars. So I'm going to go really quickly over the first 2 pillars of mitigation here, and they're fairly easy to understand, and you've been hearing about them already. So dilution is really bringing in outside air to dilute any type of contaminants. Ernie talked about a dedicated outdoor air system. That's a great mitigation technology that falls within this category. There's other numerous items here that you can look at that both CDC and Ashtray have as part of their examination of indoor air quality. Exhaust is the second indoor air quality, and that's pretty easy. It's just about getting air that may be in that kind of potential difficult areas to remove out. So you may want to have your fans on 100% of the time in kitchens, restrooms, etc. I can honestly say since last, I'd say April, May, every time I walk into a restroom now, I'm listening for an exhaust fan. So it's on my mind that much, but I now hear the exhaust fans, unfortunately. The third pillar of IAQ, and we'll go into this one a lot more, is contain, and this is really about humidity control, and Guy started getting into that. I think really people don't understand that as well, so we'll spend a couple of slides here. So why should you care about humidity? And if we go to the next slide, we'll see a really detailed chart. And I had to go a little bit engineer on everybody here, but let me walk you through this. So let's say that John Doe is the last person in your building at the end of the day. And unfortunately, John is COVID-19 positive, and he spends the last 5-10 minutes of his day coughing, sneezing, spewing into your nice building space. The amount of that SARS-CoV-2 virus that he spewed in there is initially 100%. So that's that upper far left corner. Now let's say the building space is at 25% relative humidity. That's the red dash line there. So after 10 hours, if you go down that line to where you hit the 10 hours, that's how much virus is left in the space. And with 25% humidity, there's still 30% of the virus that John Doe coughed and sneezed into your building is still active and there to potentially infect other people. But if your building's at 40% relative humidity or 50%, if you go down to that yellow and the blue line, then you'll see there's really nothing left. So the virus, the SARS-CoV-2 virus, is very susceptible to higher humidities. So you can use humidity as a risk mitigation to decrease the amount of virus that may be in your building. So why wouldn't you want to just jack humidity up higher and higher? Well, there's 3 reasons to that. And Ernie talked about one, just comfort, right? Ashtray Standard 55. It's all about making sure people are comfortable. The second is it can be hard and difficult at times to move to higher humidity in a building. And then finally, if you move to the next slide, you'll see if you move humidities up above 60%, you can get other nasties coming back into your building. So 40 to 60% is really kind of a sweet spot for COVID-19 half-life reduction. But if you go higher than that, then you can you might have to start worrying about mold, mildew, bacteria, mites, and even potentially other viruses that grow at higher humidities. So you don't want to go too high. So you want to maintain that little balance that's 40 to 60%. So let's move on and let's talk about the last of the mitigation pillars, and that's cleaning. This one is the one that people always want to focus on, but really you need to look at all 4 of these holistically. But the cleaning pillar is really about going and actively attacking these contaminants. Unfortunately, as Ernie talked about, there's a lot of claims that are out there around efficacy of devices. So we want to get into that. If you go to the next slide, what we found is that even though Trane and other OEMs have been selling indoor air quality devices for, well, decades, if you include just filtration and ultraviolet germicidal, we really headed into the pandemic as an industry without really good knowledge of how all these different technologies compared to each other. As far as we knew, no one had ever done equivalent tests on different devices with the same type of test mentality or process. Everybody had their own test. They conducted it in some shape, form, or manner that may benefit them from a test perspective. So we spent the last year doing third-party testing on multiple cleaning technologies, really to see how they compared against each other. And we looked at these in 2 different perspectives from an equipment side. One, we looked at it in duct or an in equipment like an air handler or a rooftop product that would be in the induct, or in a standalone inside the room standpoint. And then for each one of those devices, we looked at viruses. So we looked at viruses using an MS2 surrogate virus that's usually used for looking at influenza or SARS-CoV-2. And we looked at that for both airborne and surface-borne viability in terms of how well it reduces. And then we also looked at staph bacteria reduction. We did that because staph bacteria is much more difficult to get rid of. It's much more difficult to destroy. And then we looked at volatile organic compounds. Ernie talked about that a little bit. So we injected formaldehyde and toluene into our test room and looked at how well these devices did against those. And then finally, and Ernie already talked about this as well, because everybody is so concerned about ozone, we measured the amount of ozone that could have been generated from each one of these different devices. So if you go to the next slide, we'll see what our testing chamber looked like. Now, this testing chamber was 23 feet by 8 feet by about 5.5 feet high. That's not a big room at all, right? That's a tiny room for a commercial setting. But compared to most microbiological testing processes and rooms that we've seen, this is huge. Most of them that we've seen have been on the order of 10 cubic feet, not 1,000 cubic feet. We've seen some tests from suppliers that have been bread box size. What we did for this is we injected via nebulizer virus into the room. Now, for that virus introduction, we injected what was the equivalent of about 10 million sneezes. 10 million sneezes is a lot for a building, and we realize that's overkill. But the reality of this testing is it's hard enough to do in order to be able to measure the virus or the bacteria, that you have to do that type of overkill. So then for the in-room standalone devices, we measured the efficacy of these devices with both airflow and without airflow. So there was either airflow going through the room or there wasn't. And then for the in-duct testing, we conducted it at 2 different air exchange rates. And then finally, for the surface pathogen test, we had Petri dishes set up in the room that we used in consistent spaces for each of the different tests. So we used a very common testing methodology throughout all the devices that we looked at. And if we go to the next slide here, we'll be able to see the test results in comparison to each other. So what I'm showing here is that all of these are based on equivalent air changes. So it's kind of taking a look and seeing how they compare to outdoor air exchanges. And so that tells you from a mitigation standpoint, can I use outdoor air? Can I use a cleaning technology? So the blue bars that you show here really show the levels for how well airborne pathogens are reduced, whether it's MS2 or staph. And in fact, these technologies were pretty consistent in terms of efficacy, whether it was MS2 virus or whether it was staph bacteria. And the key thing to look at here is all of these technologies did work to reduce pathogens in the air. If you start diving into each one though, you see that photocatalytic oxidation device, the PCO, worked great. Ultraviolet germicidal irradiation worked absolutely fantastic. Unfortunately, it should have, because we over-designed it. You see I've got a mark there for URV 19. Usually you see most suggestions being URV levels of 13 to 14. And when we set up this test, we actually put in more UV than what we should have for the testing. But it did confirm that if you put URV at that high level, it will destroy everything. And then finally, we verified without surprise, thankfully, that MERV 13 and HEPA filters work really well. But what we found is that the last 2 technologies that I haven't talked about yet were the most interesting. The first, Ernie talked a little bit about them. We tested one needlepoint bipolar ionization device. That's seen a lot of press lately. Our testing of only one device, we only tested one device from one supplier. It showed that it did remove or reduce the amount of airborne pathogens, but it didn't do anything for surface-borne pathogens, and it didn't do anything for VOCs, so for volatile organic compounds. That's concerning because a lot of those companies have been saying it does both surface-borne and VOCs. So it concerned us a bit there. Also, from a VOC standpoint, some of Ashtray 62.1 IAQP requirements looks at potential VOCs. So if you have a device that you say is destroying VOCs as part of your standard and certification, and it doesn't do that, then you may have a conflict there. So finally, the last device that I haven't talked about are dry hydrogen peroxide devices. And they actually introduced dry hydrogen peroxide into the space. They work to remove airborne pathogens, VOCs, and surface-borne pathogens. They're the only thing we tested that did well or did anything on reducing surface-borne pathogens. But the interesting thing that we found is that this technology can continue to work across different airflows without being impacted. So what do I mean by that? Think of the MERV 13 filter, it works great. Just like Ashtray said it does, so we're not gonna dispute that. But a filter or even UVGI is only gonna be as good as what you're supplying air to. So if you're not supplying air to it, it's not gonna work. So if you move to the next slide, I've got another engineer plot for you. We took our test results and we applied a modeling, we modeled it. So Francis, if you can move to the next slide. We modeled infection rates in a classroom to compare how well these technologies work compared to each other against outside air alone. So the y-axis here is how much better it did in terms of lowering infection rate for SARS-CoV-2 than outside air. But we did this in a classroom with a variable air volume system. So this is very energy efficient because you can turn down the amount of air going into that classroom. And then we looked at it with a MERV 13 filter, which is that yellow line, against a Synexus dry hydrogen peroxide device with MERV 8. And in this case, we used a more realistic outside air exchange of 4 air changes per hour. And that was also with 3 recirculated air changes per hour. So the recirculated air changes per hour is how much air is actually going to that MERV 13 filter. So if you drop the amount of airflow rate going to that filter, then the filter can't take as much particulate, virus, bacteria, whatever's in the air out. So as you can see, when you're at that full design airflow rate, which is the far right, you see that the yellow line and the blue line are right on top of each other. So the Synexus device, that MERV 13, are doing about the same for dropping the infection rate. But as soon as you start dropping the airflow for that variable air volume system, Synexus isn't impacted. And so Synexus ends up improving over the MERV 13 system as you start dropping the airflow rate. So what I just want to demonstrate here and talk about is that the system you have in your building does make an impact on what and how you choose to mitigate. So you have to take into account what type of system you have in order to determine what your mitigation strategy should be. So if we move to the next slide, well, before I get into the management tenet of IAQ, let's stop a little bit and think about the future. We are going to get out of this pandemic. So why would we care about indoor air quality after that? The reality is that this pandemic is a generational forming event. I have a sophomore in college. I have a senior in high school who really, their last year and a half has been blown up. They're going to remember this for the rest of their lives. So you couple that with the reality So how do you tackle this going forward? Let's say you put in the mitigation. Well, what you do is you end up managing that mitigation after you put it in. And what I mean by managing it, if you move to the next slide, Francis, is you really manage the air quality and that associated risk through controls platform. And you can use those to analyze trends. You can conduct mitigation activities, whether it's dilution, exhaust, containment, or cleaning. And these controls platforms and methodologies also, if you are trying to meet well or reset building requirements, you can use those to demonstrate dates to both you and your occupants on how well the buildings are performing. So these can really help to assure that your occupants and to you, that you're working to reduce all the risks that you may potentially have with indoor air quality. So in conclusion, if we move to the last slide, just remember that each building's different and may require different mitigation actions for indoor air quality. Make sure to go and consult with a professional for a building assessment and to develop a plan that goes across all mitigation pillars. All of them are important to you and your building. And then finally, you want to have some type of controls and a service plan on how to make sure you continually update, monitor, and recommission your building ongoing for IAQ. That way you can optimize the function of your building for you and your occupants. So thank you. I think at this point, we'll turn it back to Francis just for questions.
Yes, sir. Thank you, Ron, and thank you to all of our panelists for a very informative discussion. I would ask that they would stay and answer as many questions as we have time for. I'm just going to go ahead and start off with the questions that we got, and we did get quite a few. Someone asked, how do we measure IAQ consistently? It seems like there are multiple types. And I'm not sure who wants to take a stab at that. Maybe Ernie, maybe Ron.
Well, I can start off. There's various ways of measuring indoor air quality, but typically what's done, I'll say Class A office buildings, they recommend at least once a year and sometimes twice a year or even seasonally. And what they do is we would take an airborne sample and take that sample and put it through a hydrocarbon analyzer, and that will measure VOCs, formaldehydes, and other types of molecular structures that'll give you an idea of what might be in in the environment. And one of the biggest things we concern ourselves with is formaldehyde. Formaldehyde is a major problem in carpeting, cleaning materials, things that are brand new. You get brand new furniture and things of that nature, and formaldehyde keeps popping up, and it is very difficult to take care of other than by basic dilution ventilation. And that's what that minimum outside air is really all about. We need that minimum outside air to dilute your indoor environment to keep the generation rate of other types of particulates down to a minimum.
And I'll just add to Ernie's comments that there are a lot of new sensor capability that's been generated here over the last 10 years. So VOC sensors are now available. So if you have a building control system or an in-room control system, you can have a VOC sensor that will detect that formaldehyde, will detect the toluene. There's also particulate matter sensors now. So if you're really concerned about 2.5 micron particulate matter, you can get measurements of that. And then finally, if you want to call it, the main Iaq sensor that's been around for the last 10 years is carbon dioxide. And that's more just to make sure you reduce the amount of CO2 that you have in your space. But in terms of a sensor for microbiologicals, unfortunately, we're still a ways away from that. That's kind of the golden sensor that we're looking for right now. There isn't really a microbiological virus type of sensor that's available. We would love to have that, right? Everybody would love to have that.
So we had another question regarding IAQ monitoring. So there are a number of IAQ monitoring solutions showing up in the market. And I think this relates to some of the discussion that Ron was having. Do you see these as playing a significant role, or does it need to be a part of an integrated solution? In other words, is it independent, or should it be part of the many things that we're doing to address the IAQ analysis?
Well, again, it depends on the customer. We've seen customers wanting to do both independent and integrated in with their building controls. If it's integrated with the building controls, then going forward, you can have an IAQ strategy that lines up with potential energy optimization strategy as well. And so that's where, when we see the integration of those two systems together, we see that as being really the future. You don't want to use outdoor air forever, right? You want to get out of pandemic mode. Everybody right now is in pandemic mode, but you would like to have your building controls move to where you have pandemic setting, epidemic setting, and then, hey, I've got normal building. So we're talking with customers right now about developing those controls that integrate control solutions for IAQ into what they have with everything else. And energy optimization just seems like to be part of that, because if you, God forbid, we get into another pandemic mode, we need to have that capability there, but we still want to look at it from an energy.
So we had sort of a follow-up to that in regard to just IAQ sensors in general, asking whether anyone on the panel knew if they were certified by UL or Reset for accuracy. Again, trying to determine whether they're useful in the environment, in the indoor environment.
I do believe there's UL certification on most of those sensors, but truthfully, I'm not 100% sure. I'm pretty certain that the CO2 sensors have UL certification, and I think from what I've seen from the PM and the VOCs as well. The PM and VOC sensors are a little bit newer, so I'm not as familiar with those.
This is a question for Ron. It says Ron's stacked bar chart. Hold on, it just disappeared on me. Stacked bar chart on results has surface reduction bars stacked on top of air reduction bars. And what is the significance of that? One is mainly relevant to fomite transmission and the other to airborne. DHP has a big total surface plus air, but it appears that it is not as effective as, for example, a MERV 11 filter. However, in the example on infection risk, DHP is better at any airflow. Can you clarify?
So one, the surface, the surface is just, it's big only because that's the only device that did anything with surface microbiological reduction. So and what I've got plotted there is with 6 air changes per hour. So that's a recirculated airflow of 6 air changes. That doesn't happen very often. You don't see that many air changes in general in a room. So that's a very high air exchange rate. So when you back off on that air exchange rate, it's back to that next slide that I had where Synexus performed as well, and then it performed better than the MERV 13, is because if you're not getting air back to that filter, the filter can't do its job. So when you start having rooms where, and it goes back to Ashtray 62.1, where you have a minimum amount of air that needs to be circulated through the room, and also the minimum amount of outdoor air, it's a total story of where you have to look at what the air requirements are, both from CO2, and then now if you want to look at it from a microbiological, you've got to get those microbiologicals back to that filter. If you've got a lower recirculation airflow rate, you're not going to get it back to that filter. So that device may not work as well anymore. So again, the efficacy of these devices depends on how they work and how often you can get the microbiological back to it. So I don't want to say, you know, MERV 13 is always better, because it depends on the system that you have in your building. Hopefully that answers your question.
So we had a question that talks about filtration and energy use. What is the trade-off of increased filtration and energy use? And are there any studies or pilots looking at optimizing across this criteria?
Well, I think I can probably
Army.
talk to that. The more efficient the filter is that you use in an HVAC system, for the most part, they do in fact introduce additional pressure drop. And pressure drop is resistance, which means you need more horsepower to do the job. And so what happens is it's a trade-off. You have to pay the price if you want to have ultra type of filtration. The other thing that helps out too is we're allowed to, through Ashtray 62 and others, we can recirculate air from the internal. So I can take the same air that I supplied into a room, take it back through an air handler, filter it again, and put it back out into the room. But I have to have a ratio. I can't do 100%. And the one way we do that, though, is we measure the carbon dioxide in the room, and we do what's called demand controlled ventilation. And so what it does is when it sees that carbon dioxide levels, usually they use a number like either 800 parts per million or 1,000 parts per million. If it's below that, you can close the outside air dampers. And so that's where the energy is happening. When you're trying to take air from outdoors and heat it, cool it, humidify it, dehumidify it, that's where all the money's being spent. So you cut that down as much as you can, but then you don't want to get into a problem where you start to build up indoor contaminants. And that's when you have to open the outside air dampers. And the other side of the coin now is with the CDC is recommending that these systems that traditionally use 10% outside air, whatever the total airflow is in your space, they want 10% to be outside air. It's kind of a nominal number that they're talking about. With the COVID problem, let's go to 30% outside air. That's a huge amount of outside air. And that is going to burn up energy like a lot. But so be it. You know, it's health versus have to pay for it.
Thanks for that, Ernie. We have time for a couple more questions. This question asks, bipolar ionization is the lowest efficacy in your study. What happened? It was highly touted early on.
Well, so bipolar ionization, as I talked about, it's had a lot of publicity around how well it does. Again, when we've looked at some of the test reports from different bipolar ionization suppliers, it all depends on how you test. So sometimes we've seen these bipolar ionization devices, they test in a bread box. So they'll test in a box that's 6 cubic feet. And when you put so many thousands of ions into a bread box, they're going to react differently than when you put them into 1,000 cubic foot space. So does BPI work? Yes. Does it work as well as what everybody's advertising? I don't know. The device we tested did not work as well. BPI has been around for about, they started coming out around 2010 or so. The initial BPI devices generated ozone. We've hypothesized, and we don't have proof of this, but some of those initial BPI devices may have worked really well because they generated ozone, and ozone is an oxidant, and it will work to destroy VOCs, microbiologicals. That is the good thing about ozone. The bad thing about ozone is it can cause breathing problems. So as we've pushed the industry, as our customers have pushed the industry to focus on no ozone generation, so to go to UL 867 test requirements, get UL 867 of 50 parts per billion or less, or to UL 2998, which is what we try and push now, which is 5 parts per billion or less. We wonder if whether or not these bipolar ionization devices are performing as well because there's no ozone now. So they may be working just solely from agglomeration, as Ernie talked about at the very beginning. So it all depends on which study you look at, how they conducted the study, and what did they use. So you dive into a study, and so we go with CDC here. You have to dive into the test results because there's a lot of inconsistencies here. So you need to dive into test results. If somebody says they're 99.99% against the SARS-CoV-2 virus for reducing it, I'd go read it a little bit more because they probably don't take into account natural decay. So they're throwing in natural decay as part of their removal efficacy. And then how big is the facility? If it's this big versus a 2,000 cubic feet or 10,000 cubic feet, you may have different test results.
All right, thanks, Ron, and thank you to everyone for joining us today. Thank you to our panelists for taking the time to, impart their knowledge on this very important issue. I want to let everyone know that we'll be sending a copy of the slides to all those who registered, and the presentation itself will be available on our website before too long. So thanks again for joining us. Have a good rest of your day.
Thank you, everyone.